Hello, everyone, and welcome back to the first seminar of this numerical analysis of Galerkin ROMs seminar series for the year 2024. We are very happy to have as first speaker of year 2024 Professor Stefan Volkwein from the University of Constance. And his presentation will be on adaptive reduced order schemes in optimal design and control. So Stefan, please, the floor is yours.
Yeah, many thanks for the introduction. And as you see, I'm still in the old year. So this is not a talk I gave 1 year ago. It should be the talk of this year. So 2023, please replace by 2024. Okay, so it's a pleasure for me to introduce things which are going on in our group, also together with other co-workers, and talking with you a bit on adaptive reduced order schemes in the context of optimization. There's optimal design, parameter optimization, and optimal control. Let's go to the outline. How does it work? Yeah, it's working. Okay, so I have in fact three sections, and then there is a conclusion and an outlook, of course. So the first one is something from the past a bit. Maybe some of you know, maybe for some of you, it hopefully is a good summary what was going on in the last years. And probably for some of you, it's not so known because we know there are many groups working on reduced order modeling, and you cannot keep an eye on all of these groups. So it's on linear quadratic optimal control problems. So I consider error estimation, basis update, and all this stuff. Also, there's a lot of theory which was built in the last years. Also, I have seen there are some in the audience, some people who also contributed to this aspect, and that you will see. Okay, in the second part, I will talk on something what we has done newly, especially in a DFG founded project. So where we have an optimization problem, and in this optimization problem, we do not want to have any offline phase. So nothing like for a parameter domain, compute a good basis, and they then go for a very fast and efficient ROM application, but more rather building the POD or the reduced basis, the reduced order model on the fly during the optimization. So it is more in the context we have to solve an optimization problem once. So it makes no sense to have a basis which can then afterwards be used for several PDE constraint optimization problems. And then the third section, I will talk on something what we have done currently. So it's more something what is ongoing work. And this leads me to the conclusion and to the outlook. Okay, let's start with the linear quadratic optimal control problems. There are some reference which you can found on our webpage, but of course, due to the fact that there's a YouTube video, and if you are interested, I can also send you the PDF so that there's time to look in this or find the papers. But this is only our papers to give you some kind of summary. So what are we considering? We consider a quadratic programming problem where our state constraint, let's take the cursor, is given by some evolution problem. So there is something like maybe a heat equation, or maybe what we have more in mind, something where you also have a convection part, so some diffusion convection equation, and the coefficients which are involved may depend on t, so indicated by this bilinear form which depend on t. And in addition, we also have control constraints, but simple bounds, so there's a lower and upper bound for the control in our problem. So these are the constraints, and the cost function is some quadratic cost function. It may be of this type. It may be also have additional some terminal cost. We will also have an example in this direction. This does not cause any problems. We fix on this kind of control of this kind of cost functional. In fact, it has to be quadratic to stay in this quadratic programming framework, let's say. Okay, so the state is a variable depending on time, and we suppose that it belongs to a Hilbert space. Usually it's something like H01 when you have zero boundary conditions, or H1 if you have some Neumann boundary or Robin boundary conditions, or maybe something in between when you have some kind of mixed boundary conditions. So usually V is something like H1, as I said. H is usually something like L2. So that, but in fact, in the abstract setting, you have a Gelfand triple between this V and H, and then there's also the V prime space. The bilinear form, as I said, may depend on T, and usually what you need to get existence of this of the evolution equation is something like that. You need that the bilinear form is continuous, and you need that it is sometimes called weakly coercive. So this is what I've wrote here by this inequality. So there is also this weakly, because we have this negative term here, but which the let's say which the stronger topology in front, and here at the end you have something, for example, the L2 topology. So there's some space left for a minus term in the bilinear form, in contrast to Lax-Milgram lemmas for elliptic equations. We have a control space. It is something like L2 0 T, capital T, so some time interval where we consider this optimal control problem. And then there is also some space U, for example. If you have distributed control, it is usually something like L2. Or if you have boundary control, then you have this L2 of gamma, or maybe of a part of gamma. But it may also be that you have some kind of distributed control on the right-hand side, but it only acts on 4 or 5 subdomains where you have the characteristic, let's say, shape functions. And then it is only a vector. So U of T is only a vector giving the coefficients of the control input. So it depends on the application. Input is the U, of course, and we have the cost parameter kappa. For the setting, it has not to be greater than 0, also equal 0 would be fine. But for the a posteriori error estimation, which I present later, we need definitely a kappa which is greater than 0. Then there is some kind of control operator. I do not want to be too specific on the control input. So it is maybe something which comes from the boundary, because you have boundary control and it enters the evolution equation, or it comes from the right-hand side of the parabolic PDE. Then there is also an observation operator, which is in the cost functional. So that is our setting, what we have and what we want to consider next. So optimality conditions for this are not so complicated. They are well known. It's a convex problem. So therefore, you only have to look for first order conditions. They are already sufficient for optimality. So what we have as optimality condition is, first, you have to be admissible. So your control is in the bounds. So a U bar is in U at, in the admissible set of controls. Then, of course, you have to satisfy this state equation, which is written here. This Y bar is the optimal state. For the given optimal control, it satisfies our evolution problem. In addition, there is an adjoint variable. This adjoint variable satisfies the adjoint equation, where we see on the right-hand side is the mismatch between the desired state YD in the cost functional and the let's say the result we get from the observation operator applied to the optimal state. So this the mismatch between these both. So it's in particular, if Y bar is of such a type that the observation of Y bar is equal to the YD, then the right-hand side in this adjoint equation is 0, which turns out to be that the adjoint variable would be 0. So some kind of measure, the adjoint variable is some kind of measure of the misfit between the desired state and then the state what you reach by C Y bar. Okay. Then with the adjoint variable, we can characterize the optimal solution by a variational inequality. Sometimes people call this as the optimality condition, which is in our case a variational inequality, here this VI, because we have a set U at, which is not the whole space, and therefore you get this inequality here, which means that the term here at the beginning is times this U is free variable in the admissible set minus U bar, that this is greater or equal 0. And this term can also be interpreted. So think of the state equation, which we have here, the state equation. So for each U bar, there exists a unique optimal solution. No, we have some conditions on the bilinear form. So we can use this to introduce here a reduced cost, and keep in mind, reduced does not mean something like model order reduction. It's a reduction of the optimal of the optimization problem. The optimization problem is in Y and U. And now we say we neglect, or we let's say we replace this Y by a formula, because we know for each U, there exists a unique state. So which means the state here is a dependent variable on the control. So when we replace it, then this means we introduce only a cost functional which acts on the control, and we call this the reduced cost functional. Then we can also go for the reduced problem, which means we minimize this J hat under the constraint that U only is in the admissible set, and the evolution problem is already included in the cost functional, because we only use Y's which satisfy our state equation and are indicated here by this Y of U. But here in this case, if you do some lines of analysis, you get that the reduced cost functional has a derivative, and the derivative is exactly given by the term we have here in the variational inequality. So this first term, kappa u bar minus the adjoint of the B operator times B, P bar, is equal to the reduced cost functional derivative. So therefore we can write, instead of this VI, just the derivative of the reduced cost functional times U minus U bar has to be greater or equal 0. So that is our optimality condition in one line, let's say. Okay. So again, this equation. And this equation, this inequality. This inequality is the starting point to derive an error estimate. Okay. So what's going on? So suppose we have a reduced order solution computed by some method. So I call it also U bar, but I make this L, indicating a bit that I use L basis functions, POD, reduced basis, or whatever. So some basis functions. And then what is known from theory? So there's something that what comes also from this, what comes in fact from ODE optimal control. We know that there is a so-called perturbation. I call it theta L. This is also in the control space, such that I get an inequality of this type. And look at this, I see, okay, there is this kappa u bar L, which is the same as for the infinite dimensional inequality in the first line, this VI. Then I see also there is this B star times an adjoint variable. It's also here, I see it here. But what is this PL? It's not P bar L, there's a tilde. Maybe, hopefully you can see it. And this comes here. Aha, okay. I have to solve the adjoint equation, and I mean the full order equation, which means, in practice, the finite element scheme. So let's say the high fidelity model for the U bar. So this means you take the U bar L, the optimal reduced order solution, you solve the state equation by finite elements, then you solve the adjoint equation, finite element, so two finite elements solved. Then you have this P tilde L, and then you can substitute it here in the variational inequality. And then there is this theta L. Okay. So what can I do with this? So why we are doing these things? Okay, look at the next lines. So the idea is now, in the first variational inequality, we can use any admissible control. So one possibility is that I choose the suboptimal reduced order solution. So I take this U bar L in the VI. And vice versa in the variational inequality with the perturbation. So this VIL, I have again this U here admissible. Here I use the optimal, in fact, unknown U bar. So this I put in there. Then you see here you have in the first variational inequality, you have something like, you have something like U bar L minus U bar. Whereas in the second variational inequality, here, I mean here, you have u bar minus u bar L. I add both, I get a minus sign, and then fighting a bit with these things, getting us to this error estimate I wrote here in blue. So the optimal unknown u bar minus the suboptimal u bar L, which is computed, for example, by a reduced order scheme, can be estimated by the norm of the theta L divided by the kappa. Okay. Yeah, what about the right-hand side of this estimate? There's a theta L, and this theta L can be computed. Okay, here is the formula. And we see that there is this term here, which reminds us is the same as here. This is nothing else but the reduced gradient, what you had here, evaluated and at the suboptimal control u bar L. And as you see here for this evaluation, you have to compute this P tilde L. Okay, that's it. And for the other part is for the active sets, because it's not only the question if you are, what is the distance, you also need to estimate in this distance the error between the active and inactive sets. We not only compute a control, we also compute active and inactive sets. And the question is also, is our reduced order scheme good enough to get an active set corresponding to the suboptimal solution, that and also an inactive set, which is very close, hopefully more or less equal to the one we should have for the optimal solution. Summarizing, for the computation of the theta L, we still have to do, in this case, here some computation with finite elements, but it is not necessary to compute the optimal solution u bar, because it's not necessary to have this guy. It's only necessary to solve successively state in a joint equation with finite element. You can look at the work of Kercher and Greppel, where you can find also ideas where you avoid this computation of the finite element and work more on this a posteriori error estimation from state and a joint equation. Also do it for the active and inactive sets. But I keep it like we have it here and go further. So why are we doing these a posteriori error estimation? So maybe I do not have to convince you, because when you have some reduced basis community, then of course you are used to build a posteriori error estimation. But at the beginning, we came from the POD from the POD stuff. And what is the bottleneck of POD? The bottleneck of POD is that the basis that you compute can only be as good as your snapshots are. So if your snapshots are bad or not well chosen, then you cannot expect that you have a basis which is a good approximation. From, let's say, from the functional analysis, we know, okay, at some end it spans the whole space, but we from the reduced order community want to have that, of course, not in the limit that we get the solution. We want to have a good approximation for very small number of basis functions to get the speed up what we want to have. And also we in the optimization want to have this. So here I've wrote this. So there is an a priori error analysis for POD. So we can estimate really the error between U bar, the optimal solution of the original problem, and the corresponding reduced order one. And the error you get is something, okay, there is a prefactor, but look at this, it has something to do with the eigenvalues of the POD mode, for the POD snapshots. And these eigenvalues, of course, they decay. And you get here something like, okay, it looks not so bad because we have decay if the lambda E goes fastly to 0. But we only have this estimate if we look for this kind of snapshots. And there you see, hey, there's everywhere a bar. So which means you have to know the solution. Then you can build from the optimal state and the optimal adjoint a basis, and then you know that you have this kind of stuff. But this is something from theory, nice to have, but from practical use, You don't want to have the solution U bar to compute a POD basis and then recompute a suboptimal solution. And therefore, we need the a posteriori error estimation, and we do it like this. We take some U, run the state equation to get snapshots, run the adjoint equations to get snapshots from the adjoint. From both snapshots, we compute a reduced order scheme. Then we use this to reduce our optimal control problem, which means we have a Galerkin ansatz, as you know, then we reduce the state equations. We also plug it in the state in the cost functional and get a reduced order scheme. Then we solve this because we have these control constraints. We need something like, for example, semi-smooth-Newton method, some kind of primal dual active set strategies to take care of the constraints. Then we get a solution. This is, of course, depending on the basis you have chosen. So we want to estimate, is our suboptimal control good enough? For that, we have the error estimation. So we solve the state equation with finite elements using the computed suboptimal POD or reduced order solution. We compute the solution of the state equation, then the adjoint equation, set up our perturbation. As you know, let's go back here. We have the formulas. We have the formulas for the theta L. Okay, with these formulas, we look here in this if loop. Is it small enough, depending on these factors, norm of theta divided by kappa? And if not, we enlarge L. We take more basis functions. And what we take into account, I'll go back, is what we have here, that for L to infinity, we have that the theta is going to 0, which means the norm of theta is going to 0. So at some L, we expect that this is small. Of course, what we do not have is any rate. It's not clear how fast this theta L goes to 0. Probably for some specific heat equation stuff, you can do something. If there's a convection, you cannot get a rate there, up to my knowledge. So then we enlarge L and solve again. And at some point, we hope that the factor is small enough, and then we are happy. So we solve probably several times the whole optimization problem, but we trust on the fact that we only use not so many basis functions and therefore stop at some point, and it is not too costly to solve it several times. So we should have a look to an example. I just want to pick out the main things. So what we do here is I take a heat equation. We have boundary control. So it's a Robin boundary control. We have control constraints. What do we see? We see here, hope the full is very small. This is the decay of the basis of the eigenvalues of the POD computation. 2, okay. 1 is for taking the stiffness matrix, taking the H1 norm, computing the basis. Remember, there were some norms in the POD computation. And the question is, what kind of norm should we take? So one option is, of course, H1 in this case, because we have Robin boundary conditions. And the second choice is, of course, taking the L2 norm. And the L2 norm gives you a faster decay because the L2 norm is weaker than the H1 norm. Of course, then the decay is not as fast, but we see in both cases there, for this example, this is heat equation, very fast. So then there are 2 plots. We see here 2 plots, on the left and on the right. What's this? Okay, the right one is the optimal control at 4 different time slots. We have in this case, we have the optimal control, and we use the optimal control to build the basis. So, which means in this case, we have the optimal solution. On the other case here, we use some expected control. So the left-hand side is used to build the basis. The right-hand is used for the optimal solution to have a comparison. How good is our basis? So let's have a look for this table, and then it becomes hopefully clear to everyone. So we have two examples here, two runs. You see here the number of basis functions. Then the left-hand side is computed by choosing the expected control. The right one is I compute the finite element solution and use this information to get the best basis. So which means the ideal case. What do we observe? Yeah, of course, as the a priori analysis says to us, if you have the optimal state, the optimal joint in the snapshots, you are in the best situation. And that is what you see here. Also here for 60 basis functions, also for 20 basis functions, the efficiency is more or less 1, which means the error estimator reflects exactly the behavior of the error. Looking in this the left part of this table, we see it's also not bad, but not as good. We see it's fine. We see also that the factor is not going smaller, enlarging the number of basis functions, and that leads us to the observation. This is only heat equation. I could also show you other examples. The choice of the optimal control the choice of the control to build the basis is essential for the behavior of the optimization method. So which means it's not only necessary to increase the number of basis functions, at some point it's necessary to change the basis, not only to increase the number. And that is something I want to tell you on the next slide. So let's say beginning there. Okay, so what are we doing here? So it can be, these things can be extended to nonlinear dynamical system. Therefore, I write it in an abstract way. See here, I have a dynamical system, right-hand side, and it is maybe nonlinear in y and u, of course. That is what I want to show you here. Then we have also bilateral control constraints, and we have a cost functional here. So when we do reduced order modeling, what are we doing? Okay, what we do is we take a basis, for example, POD. We can also take reduced basis. We also can take Down's truncation and take the basis from there. And then first we reduce our dynamical system, here indicated by this L. No, there's a new FL, maybe dime is included, things like this. So it looks like these formulas we have here. Also, the cost functional has to be changed. There's a numerical integration. We use also there the reduction we have done for the state. So I go further. The POD basis in that case, I wrote you POD basis of rank N, L, is computed as we did before. We solve the state equation for some U, and then we use these snapshots to build a basis. So we solve these so-called eigenvalue problems, and the solutions are given by this POD most. These are the psi i's. Okay, the idea now is the following. We want to choose not any basis, psi I. We want to choose a basis which directly is associated with the control iterate we have at hand. So which means think you are at an iteration and you have the control U. Then what we do is we solve the state equation for this U. From the state equation, we solve the eigenvalue problem. We get the psi's. Now the psi's depend on U. Also the eigenvalues depend on U. If you change U, you would get a different state, and the different state gives you a different snapshot, and the different snapshot gives you a different basis. So then we have the basis, and we use exactly this basis to do the reduction. Okay, this sounds maybe nice because now the basis is directly related with the control problem or with the optimization problem. But there's something which confuses me a bit, because to get this, there is this here. So which means the problem is more complicated than the problem we had at the beginning. Because to solve this problem here, we have also to solve the state equation, which we want to avoid, to solve it on the finite element level. Okay, what is the intention here? The intention is this. We don't want to solve this full problem. What we want to do is we want to find, let's say, by applying a few gradient steps, a better U, and then continue as we have described for the a posteriori error estimation. So what we do is we augment our problem PL, the reduced order problem, by our constraints. So we have this eigenvalue problem, we have the state equation, the full order state equation, and then we continue to derive a gradient for the full system. And then the idea is just 1, 2, 3 gradient steps on the full system, and then we stop. Take this U, compute the basis, what we do already, and then we fix the basis, and we do this, what we have explained before, just increasing the number of basis elements, and hope that these steps here are maybe costly as the beginning, but we get a control which is then better than some control, some expected control, which comes for a complicated problem, usually not through the door. It's that difficult to get this. So, and I show you one example here for some numerical example. And for that, I go back to the quadratic problem, but make the problem a bit more complicated. So the cost function, when I look at this, it's still quadratic. Terminal cost is from the optimization problem a bit more complicated because you don't have the let's say the coercivity on the full space, you only have it at the end. This is something which is more related to the control, to the optimization method. But look at the constraints. The first line is as before, state equation. Evolution problem, right hand side you have this BU as we had before, but now we not only have control constraints, we also have state constraints. Oops, state constraints, how to handle this. Okay, what we do is Lavrentiev regularization. We add 2 further parameters. They are positive. And the idea is this, look at this. We introduce an additional variable, some kind of artificial control, and put it here in this way, this epsilon W. And the idea is, look at the cost functional to have W very small because we minimize it here. It's part of the cost functional. And so the idea is, of course, if epsilon is small, and also after this minimization, we hope that W is small, then this what we have here is a good approximation of the state constraints we have one line above. So that is the idea. So some kind of approximation of the state constraints. And the essential point is that this problem we have here can be written as a control constraint optimal control problem, where now the controls are U and W. There are several lines on slides would be necessary to explain this. Please believe me. But in this case, you have regular Lagrange multipliers, and therefore we can apply the theory from the beginning. So that is interesting. So we can go for state constraints problem, and look at this. What we have here is an example. If we still have, we take the heat equation, we have some control on the right-hand side. And as you can see from this plot, there is a region where we touch the upper bound for the state constraints. So the state constraints are active. You see also the control is given here. The control try to put the state on some height, so to have these positive values. And then in the middle where you have this flat region, we stop the control. Therefore, you have this behavior here. It's not a very smooth control, as you can see. So stop the action. And then there's still some action needed in the middle. You see there's some bump here in the middle. And this is the optimal control. So when we solve this by finite elements, you get a basis, which is exactly what you see here, the first Anders function. So again, we have this problem. We solve it with finite elements. You have snapshots. With these snapshots, compute a basis. And you see the first BOD basis functions here. The question is, when I start with this OSPOT, is it possible to get something like this? And it is. So we start with U equals 0. And then we did this OSPOT stuff. We did 3 gradient steps. And then we get this basis, and look at this. The first basis, they more or less coincide. The second also, the third also, and also the fourth is not so bad. So we are very close to the exact POD. And it turns out that taking this basis here in the last line and do this a posteriori error estimation. Now we fix the basis and just increase the number of L, gives us the chance to compute an suboptimal solution which satisfies the tolerance condition U bar minus U bar L is very small without computing the U bar. So just again, for this OSPOT, we don't compute the U bar. I only compute it to get this middle, the middle column, to show, the middle row, not column, the middle row, to show you this would be the optimal basis, the basis. So just to see how good the OSPOT basis is in that case. Okay, so that is the optimal control of quadratic stuff. And now I turn to my second part. And as you see, this is on trust region methods for PDE constraint optimization. And the idea is now a bit different. So we are looking for a parameter in this PDE. I don't specify it here. And just to make the point that at the beginning, usually what people do is they start a greedy. And in our case, look at this picture here. We have two parameters here. And what is built here is the cost functional. And to get a good approximation of the cost functional, we run through the parameter space. And as you see, there are several values taken and build a reduced basis approximation of the cost. Okay, but for that, we need several parameters. In the optimization, that is this here, we see it's not necessary to have a good approximation everywhere. The optimization loop is doing something like it starts here, then the second iteration is here, the third is here, and then there are some iterations you cannot distinguish. They are here at the end. You stop here and say, I have solved my problem. And a good approximation here, for example, is not necessary to get a good behavior or performance of my optimization methods. And then you see these bubbles here, or these circles here. What does it mean? It does mean the following. You start with, of course, finite element. You do a first step. You get the basis from this finite element solution, do the reduction. Then you work on the reduction and you observe, oh, my reduction is not good. I have to include more basis functions. Okay, you stay at the parameter. You do not trust your approximation. You increase the basis. And that is indicated by this staying at the same point. Many bubbles means you stay there. You are not doing the next step in the optimization. You build the model. At a certain point here, it's indicated now you are satisfied. Your model is good. Your reduced order model is good. Let's do an optimization step. You go here and you observe, okay, it's not good. Maybe one update, use the parameter here to improve your model. It's fine. And then the same here, only one update. And maybe here's one update necessary. And then you are in. So the idea is we want to build the basis on the fly, but only on the iterates which we touch during the optimization method. And at the end, we have a suboptimal solution with a corresponding reduced basis. And of course, if the problem is really complicated, it may happen that at the end you have a result and a solution, but also the message, we have not used the reduced order model because it was not possible to get some reduced order model for such a complicated problem because there is maybe this limit. You don't want to use more than 40 basis functions or 50 basis functions. At the beginning, we cannot have an estimate if 50 would be enough for the underlying problem we have at hand. So that is the idea. So we have a surrogate model by the reduced basis. It's only necessary that this surrogate reduced order model is good in a neighborhood to have a good estimate of the descent direction for the optimization. And in the trust region model, it looks like this, that you have the trust region radius here, and the error is quantified by error estimation. So here you have the error estimation, the a posteriori error estimation of the cost functionals, which of course depends on state and adjoint information. And this gives you the problems you solve. And the surrogate model is the reduced order model here, where maybe you stay at some point and you say, we are not good, then we have to increase the reduced basis space to get at the end a good approximation so that this factor here is below this trust region. So when we go back in the literature, then you see their first work in this direction is for POD, for this trust region POD, not with this error estimation in the work Arian, Fahl, and Sachs. But there's also this work, this is a new work, and this was also the starting point for our works, the work of Kian, Greppel, Verroy, and Wilcox, who did this with BFGS updates, and this was also a good starting point. So include this here. So if you want to read more on this, please have also a look at this paper from 2017. Okay. So we apply this to this problem. So this is a coupled problem. We have a parabolic equation and an elliptic equation. The parameters are only this mu1, which is here, the mu2, which is in front of the f, the mu3 here, and the mu4 here also in front of the f. Both f's are the same. They have different signs. And the nasty thing is that this f is really not so nice. So it's not monotone. It has the square root in, it has a sinus hyperbolicus. So not a nice thing where you can do a posteriori error estimation by analysis. And therefore we use another technique here. I come to this in a minute. Okay, so this model comes from this battery system. So Y would be something like concentration of lithium ions, and the Q is the potential in the battery, but it is still a simplified model. So I do not want to write model for lithium ion batteries, but it is motivated by these by battery models. Okay, parabolic and elliptic. We have 4 parameters. And as you see, there is also a U, but the U in our case is fixed. In fact, we use this also for optimal experimental design, where we play with this U to have a better estimation of the parameter. But this is not the issue today. So just to mention this. We have the strong nonlinearity, which is non-monotone, which is not good for a posteriori error estimation. So that I have already mentioned. So you can do some theory on this on small time interval, because we have no restrictions on the initial data. Then we can guarantee that this coupled system has a solution. I go further. So what we have is the finite element model, the full model, and we have the reduced order model. In our case, it's a reduced basis model, what we use for the reduced order scheme. So we have time instances, so 1 to k. So there is something for the y variable, for the concentration, let's say. The q variable is for the potential. There's some difference. You see here's n and n0. This comes from the fact that the q variable is fixed on one boundary. This is due to the fact that the potential usually is not unique. To make it unique, you have some additional constraint. And in our case, we've just fixed it on one side to be 0. The reduced order scheme looks the same. So we have some smaller spaces, this Ly. Of course, we need something like discrete empirical interpolation methods to handle the nonlinearities. We have a basis for the y. This is this VL. We have a different basis for the Q variable. So we have Ly and Lq as the number of basis functions in both spaces. And this gives us this reduced order approximation. So the idea now is, okay, we cannot derive an analytic estimate for this case. So on the other hand, need for the trust region error estimation. For the trust region, I showed you, there was this error estimation of the cost functional. So we need something. So the idea what we are doing is we use hierarchical error estimation. And what we are doing there is we have a second basis. So we have 2 bases. One is smaller and the other one is larger. So which means it's something as a low dimensional reduced order space and a higher dimensional reduced order space. And that can be used in such a way that we say the larger space is closer to the high finite element finite element spaces, but it can still be evaluated very fast because it is still small in contrast to the finite element. And then there's the reduced one where we carry out the optimization. So which means to evaluate the error estimators, we play with this higher and lower dimensional spaces, and it helps us to get error estimates for this complicated case. But keep in mind, these error estimators are not certified. They are not certified because we cannot, here, look at this. This means here, this here, M, this means the error between the finite element and the reduced order one is smaller than epsilon. This would allow, when you cannot do an error estimation for this term here, would allow that you should know. No, this we have not. So, and therefore we use the a posteriori error estimation here, but in our case, it's not certified, but it does a good job. So that is what we observed for this nonlinear stuff. We have works where we use certified error estimations. Go back to the first slide on this chapter. This was the co-work with the group in Münster. But look also in the Kian paper, there's also, they use certified estimates because the equations are not of this type. You don't have these non-monotone and non-monotone nonlinearities. That is the difficult part here. So there's a saturation pair. I've had a look at the time, so maybe I do not spend much time here. I just go for this, just to give you this hint and maybe make you curious that you look in the paper or ask me afterwards, that we are in contact also after this, after today, you can contact me. That you see in our cases, that we see, of course, this is something we know from reduced basis, that evaluating the PDE can be sped up a lot by this reduced order scheme. So it's from 8.5 seconds to solve the equation, this coupled system, compared to 0.1 for the ROM. But also the parameter estimation is running very well. The finite element solver needs 1,700 seconds, whereas the ROM only needs 1/10. We don't have this factor like 100, but keep in mind, there is no a priori computation of the reduced basis. It's done on the fly. So that is the message of this chapter. Do this computation on the fly when you are not interested to have a reduced order basis for several optimization problems. I stop here and just give some remarks on this, on the last issue, what I have here. Okay, so what is the goal now? It's a related, but a bit different topic. You see heat equation plus some reaction term here, and we also have this convection term. And you see on the right-hand side, we have subdomains, maybe some squares in the domain, and you have controls, ui of t, okay, by finite many controls on the right-hand side, you try to influence the state. And how to influence it? I want to influence this in such a way that I have a stabilizing control, so that my y of t is going to 0 if t goes to 0. So that is something what I want to have. For this equation, it's time varying, it's still linear equation, but on the right-hand side, I have finite many controllers, and I want to stabilize this system. And as you see, RH stands for receding horizon. I use some model or some model predictive control strategy to compute this control doing this job. Okay. So the performance index is like this. So I want to penalize the gradient. YU means you have the solution to the state equation for given U. So I take the U, solve the state equation. This is the YU. So I penalize this. And then the interesting thing for us, at least, was that we use here an L1 norm. L1 norm means not differentiable in the standard way. But with this motivation, with this L1 norm, you get sparse controls, which means at some parts the control is in the interval is 0. So it's like you mimic a bit a switching control in this way, you know, without going for mixed integer stuff at that point. No, we stay still in an analytic way, take a non-differentiable, classical non-differentiable norm, but with this we get sparse controls, which means sometimes they are on, sometimes they are off. That is what we hope, and still want to stabilize our problem. The infinite horizon problem is like this. You have an initial condition, you start at 0, and you try to find the u over the whole domain from 0 to infinity. And that is usually something what you cannot do, because due to the fact that it's an infinite horizon, and also finding this control is difficult. Therefore, we go for a finite time. This is this yt here, the yt. And on this interval from some initial time to this t0 plus t, so t is the time horizon, we look for an optimization problem. So this is an finite time horizon, so it can be solved by, this is linear quadratic, by stuff we have done at the first section. So this can be applied. So that is the idea. And again, here's this finite horizon problem. And what we do is this, what I mentioned, receding horizon control. So you are at 0, you have the time horizon capital T, you compute a control for this time interval, and then you take this control and apply it to your state equation. There you use really the finite element approximation. You plug in the, let's say, the control you have computed, but only for one time step. Then you switch your time horizon to delta t, or to this delta, and again take this horizon capital T, solve again, take the first step of the computed control, apply it to the system. And the hope is that with this successfully computed controls, my y goes to 0. That is what I want to have. No? And it can be done. So this is in these slides. It's some theory. So we can prove that there is stabilizing, that if n is sufficiently large, if this delta satisfies certain conditions, and also the time horizon satisfies certain conditions, we have stabilization. And in addition, that is the previous theorem, the first one, there is a way to compute this using the prox operator. This is due to the fact because there is this non-differentiability, but you can still compute subdifferentials, and in the subdifferential, it's easy to find by this prox operator a representant which ensures convergence. So that is interesting. So we can solve this non-differentiable problem. And then we have also some theory which ensures that we have a stabilizing control. So what is the new aspect what we are doing? This here, what is written here, is on the infinite dimensional level. And now we want to do this on the reduced order level. So we compute a basis, and our observation was that in this case POD, but you can also go for a reduced basis for a POD greedy approaches. It does a very good job. So in fact, we have 13 subdomains here. For each we compute the controls. So therefore we have these, you see here, these 13 controls over time. This is what is plotted here. And if you look for these results here, you see, first of all, if you do nothing, if there's no control, you have blow up. If you now start to do the receding horizon, something happens what is known from model predictive control. If you make the horizon longer and longer, the control is becoming better and better. So the longer the time horizon capital T is, then you get more decay of the problem. So that is something what is known from model predictive control, and it is, let's say, reflected by our computations. The reduced order scheme works very well. So if it is not good approximated, not enough snapshots, okay, we still have blow up. But after a certain value, we see that the reduced order scheme is running very well. And we also see that there, what is here? You see these broken lines here. It reflects the case of sparse control. So sometimes the control is switched off on, and we get also that it is doing a very good job here. So we reflect the finite element behavior very well. And what you see also from the computations, we are much faster. So you see here the finite element solves. So you see just look at the numbers and compare it with these numbers you have here. So you see there is really a very constant number here. So it seems that this corresponds to different time horizons. So there is not much impact, whereas the finite element solver is becoming more and more fighting with the larger horizons. Okay, what's going on? You have this finite time horizon, and if you enlarge it, of course, then the number of variables the free variables is increasing, and therefore the finite element solver needs more. In our case, with this reduced order approximation, the increase is not so big. So therefore, there's only a small increase in this from 0.3 to 0.5. It's doing a very good job. So in fact, coming to the last line, we have this a posteriori error estimation on basis adaptation in the first section. A lot of theory, it works very well. There is also references in other groups. It's a way how to use reduced order schemes in linear quadratic control. Keep in mind, all this stuff can be done for time-dependent coefficients, so not for like balanced truncation where you need time-invariant linear quadratic problems. So then we have this reduced basis approximation. When you want to have an approximation where you don't want to spend much time in an offline phase, then of course this online computation of the basis might be a thing you can think of, and have a look on these trust region approaches used in the Kian group and in our group. Then the next step is this stabilizing control, and that is something where we are also currently working on. We are now want to make a certification of this stabilizing. So we have this certification for the finite or infinite dimensional stuff, but in the next step we would also like to have that by using the reduced order scheme, we still can give certification by our method, so that we have the decay that when the reduced order scheme is sufficiently accurate, everything is fine, and we can have theoretical foundation of the method. Of course, where we are also working on is the case, especially in the direction of parameter estimation, that the optimization I showed you in the second section is maybe not on 4, 5, 6 parameters, but on a space of parameters. And then this means you have also there the problems of efficient evaluation of a posteriori error estimation, because you have the full order parameter functions. And there we also work on this a bit to get an idea to come up with solutions. And I thank you for the attention. And if you want to look for the publication, you find them on our web pages or the links to the journal papers. Thank you for the attention.
Thank you, Stefan, for the presentation. So now the floor is open for questions. So if you have a question for our speaker, just feel free to unmute yourself. Or if you cannot unmute yourself, you may also write in the chat. So let's see if there is someone who has a question.
I think I still let the slides there, but of course maybe we have to go back to them.
Because they might come in handy.
Yeah.
So I don't see any raised hand or people that are unmuting them. And maybe I can ask if you can give us a hint about this second outlook. So what would happen in like the second part of, or what changes would need to be made in the second part of the presentation? If the parameter was a dimensional, or let's say the control was even infinite dimensional, so it was the function.
So what we have tried so far is the following. So think that you do a parameter estimation, okay? And you have a typical diffusion problem. So there's something like divergence of Q times gradient your state. So, and the Q variable is a function. Then, as we said, we can do a reduction of the state variable. We can do the reduction of the adjoint variable, but there's still the Q which lives in the high dimensional space. So we have a lot of finite element Ansatz functions which slow down the evaluation of the a posteriori error estimation. So one idea is, of course, to introduce also an approximation for the Q space. So what is a good basis for that? So when you look at the literature, there is some work done, for example, by the Quattaroni group, where they have a linear quadratic problem. And in that case, they end up with a saddle point problem. And also there, they reduce this by using techniques as we know from saddle point problems. And this gives you automatically also a basis for the control. In our case, this is not so easy because we have a nonlinear coupling. So we have this Q times state variable. So one idea what you can do is you can use the optimality conditions. In that case, usually what you have is that from this, maybe I can go back. We can also use these first slides on the linear quadratic just to get the idea. There were the optimality conditions. Here is the optimality condition. Yeah. So think of this problem here and think of the case that you do not have constraints. When you do not have constraints, then the variational inequality turns out to be just gradient equal to 0. Now, that is usually when you don't have control constraints, then the optimality condition is gradient equal to 0. No, this case. So gradient equal to 0, look at this formula here, means that this term is equal to 0. So what you can do is, okay, if you have a basis for the P, then you can get from this a basis for the U, no? Because you have, this has to be 0. For P, you do a reduction, so it can give you an idea how to get a reduction for the U, but just apply the B star to the basis you have computed, for example, for the state. Does it give you some idea?
Yes.
Yeah? So just use the optimality condition is something what we did for the parameter estimation problem, and now we want to also transfer this to the optimal control stuff.
Mm-hmm. Okay. Let's see if there are other questions from the audience.
No, I think also please feel free to also to contact me afterwards. I think also there are different topics, so maybe if you have a specific topic, maybe it's more in section 1 or 2 or 3, contact me maybe before you start to read all papers. Maybe it's better to have a short call, and then I can give you maybe some tips how to go through these things.
Okay, so I think that we will take you up on that offer if if needs arise. And so with this, I thank again our speaker, Professor Stefan Volkwein, for his presentation.
Grazie mille.
And I'll see all of you next week, same day, same time, for the second seminar of the year. Thank you.
Ja, ciao. Buona
Bye.
giornata.